Hey kids, time to do some more inverse work. So you want to title your notes here, Derivatives of Inverses. Now, we just spent some time learning about particular inverses, right? I gave you a formula for all the inverse trig functions. But what if you just had any old inverse? So for instance, look at this algebra 1 parabola, but I've restricted the domain so that we only have half of the parabola, meaning it is 1 to 1. Therefore, when I take its inverse, the inverse is also a function, right? Notice that if I just take the derivative of x squared, I get the slope generator function, which is 2x. If I plug in 2, right, plug 2 into the function, I get the point 2, 4 on this graph, right? 2, 4 is on the graph. If I want the slope at any x, the slope at any x on x squared comes from 2 times the x coordinate. So it just so happens that the slope is also 4. The y coordinate and the slope in this instance happen to be the same. So the slope of the curve at 2, 4 is 4. There's the red is the tangent line. Now, I want to find the inverse of this function. Number 1 fun fact about inverses, x and y are switched. Number 3 fun fact of inverses, inverse functions reflect across the line y equals x. So here I go with my algebra. Y is equal to x squared, switch x and y, get y by itself. I only need the positive square root of x because I restricted x to be greater than or equal to 0 there. And I wrote the rule for the inverse. Now, if I need the derivative of the inverse, this is easy. I can just find the inverse rule. Easy to find the inverse rule, and then I'll take its derivative. There's the graph. I'm going to find its derivative. Right? I took the radical off and rewrote it as something to the 1/2. And then I'm just going to use my power down rule. 1/2 x to the negative 1/2. I could write it like that, doesn't really matter. But notice what happens if I ask you for the derivative at 4. From the domain of the inverse. But remember the number 1 fun fact about inverses? Domain and range are switched, right? So notice that on the original was 2, 4. On the inverse is 4, 2. Check out what the derivative of the inverse is. Hey now. The derivative of the inverse at a domain value of the inverse, but remember, this used to be a range value on the original. Right? The range value on the original became a domain value on the inverse. The slope of the original was 4. What's the slope of the inverse at the flipped point? Whoa. Check that out. So this is a neat thing to know. It is not critical that you know, especially because, as I said, for a whole bunch of functions, it is easy to find the inverse rule and then find the inverse rule, then take the derivative. Right? Sometimes, though, it is a pain to find the inverse rule, or sometimes I'm not given the original function, I'm just given some information about it. I'm asked for the derivative of the inverse. So we're going to use this handy-dandy relationship. The slopes of the curves are reciprocals of one another when you have inverse functions and you switch the x and the y. So this pattern always holds. So yes, you want to write this down, but this is down on your list of things to study, right? This is tested in May by AP. It's just not heavily tested. Right? The chain rule, you got to know. So here's what this says. Let's break this apart. The derivative of an inverse function. The derivative of an inverse evaluated at a range value from the original. Right? If 2 is A, 4 is f of 2. When you take the inverse, the number one fun fact of inverses is switch x and y. So what used to be a range is now a domain. What used to be a range used to be a domain. Right? What used to be a domain is now a range. What used to be a range is now a domain. So the derivative of the inverse evaluated at a range value on the original is the reciprocal of the original derivative. Original derivative evaluated at, right? That bar means evaluated at the domain value from the original. So how would that look here? What if I said to you, what if I hid x squared? What if you didn't know that you had x squared? What if I said, hey, given a function f with 0.2 comma 4, and f prime at 2 is 4, what is the derivative of the inverse evaluated at 4? So you don't have a picture, you don't have a function, so you can't find the inverse rule. but you know that this is a domain on the original, this is a range on the original. So, since I know that f of a, the derivative, right? They're asking me 4, remember, is f of a, right? 4 is the old range. The derivative of the inverse at what used to be a range on the original is not 4, but is 1 over 4. I know that's a little weird. Let's try a couple more. The derivative of the inverse evaluated at the old range is equal to the reciprocal of the original derivative evaluated at the original domain. So remember, f prime at 2 was 4. So the derivative of the inverse at the old range 4 was that slope reciprocated. So here's how AP might test you on this. They didn't tell you what f is. They just said, I have f of 3 is 5. So you think to yourself, 3, comma, 5. A, comma, f of a. Domain, comma, range. The derivative of the original was 6. They want to know what the derivative of the inverse is at the old range. Used to be a range, is now a domain on the inverse. It is not 6. It is 1 over the original derivative evaluated at the original domain. Okay, so AP likes to test you this way. This is actually more typical than a standard regular problem. Let me show you that. Oh, I forgot. I had that again. So here's what a more traditional problem might look like. And a lot of your homework problems are like this. These just don't show up as often on a test in May, the AP test in May. So notice I've given you an original parabola with a restricted domain. So that function looks like that. And I'm going to give you a point here on the original. I want to write the equation of the tangent line to the inverse graph at another point. So, step 1, I could find the equation of the inverse, but I promise you I'm going to go through this problem slowly, but it's actually going to be faster. Find the derivative of the original. That's an easy derivative to do. Evaluate the derivative of the original at the x value that I give you. I haven't given it to you yet. It's going to fly in there in a minute. Then reciprocate your answer to 2. Then write the equation of the tangent line. So there's the point. So the reason I step these out first is because if you just look at these words, you might miss the shortcut. Again, I could take the derivative of this. I'm sorry, I could take the inverse of this equation. It's not that hard. I could find that derivative and I could find the slope at -5, 1, and then write the equation of the tangent line. Or if I remember my derivative of inverses shortcut, finding the derivative of 2x squared was very nice. Evaluate the derivative at the original domain. Reciprocate that answer because the derivative of the inverse evaluated at x equals the old range is 1 over the derivative of the original at the old domain. And now, hello, done. There's the graph of the original. There's the slope of the tangent at the original at 1 comma -5. The derivative of the original at the original domain. Use my inverse little shortcut. Write the equation of the tangent line. Again, if I forget that neat little fun fact, as long as you give me the original, I can just algebraically find the equation of the inverse and then differentiate, right? I do know how to do that. The old range is the new domain. That's what that graph looks like. There's the tangent line. I do have to remember the chain rule, bring the 1/2 down, copy over the middle, subtract 1 from the exponent. Don't forget to spit out the derivative of the inside. Plug in -5, but guess what I'm going to get? 1/4. So this wasn't terrible, but it was more work and a little, especially if I forgot the chain rule, I would get the answer incorrect by not remembering my cute little shortcut. So the handout that I've given you has all of these problems on it. The nice thing is that there is a website that's also printed on this handout, so that when you click the solution key, this little button here, it takes you to a stepped out solution, right? So that's really nice for you to be able to look at. So I do just want you to copy the problem over and find the equation of the tangent line to the inverse at the given point. Now remember, the given point is on the inverse, and I think you can figure that out, right? If you plug 10 into here, you certainly do not get 1. 10(1) is not on this function, but 110 is. Right? So you do have to remember, this was your original A, this was your original f of A. So let's do the first one together. Find the derivative of the original at the original domain. The equation of the tangent line then is the point on the inverse, because now, right, this is your x and this is your y on the inverse. Take the slope you found at the original with the original domain and flip it. Done. So notice that for the number 2 is a polynomial. Number 3, you have to know your e to the rules, right? And chain rule right there. 5, this is a product. So you have to remember your product rule as well as your e to the chain rule. This is a quotient rule with a chain rule in it. Chain rule, power down, linear, chain rule here. Regular arctangent. You do need to know that arctangent is the same as inverse tangent of x. And that's being squared, so that's certainly going to take the chain rule. And lastly, 7x cubed plus chain rule. And the derivative of ln, right? Which I taught you in a previous video. All right, but again, if you go to the website on the handout, it will take you to this website where this, you can see this is where I got the problems from, but notice I can hit the solution. Right now, they leave y's in here like this. I don't particularly like that, but whatevs. Just remind you to put in the y value that they gave you. Right, because their y, they're giving you the y that used to be the x on the original. Okay? All right, I will see you in our live session.